This handle on a container will be simulated and then geometrically optimized using a design study in SolidWorks Simulation. I don't have any original drawings of the parts, so the model you see here is going to be built on the given picture and the problem description. One interesting question is why the handle is curved and not straight. Was it originally designed this way intentionally, or was it deformed under loading? That's something we are going to analyze in this study. The goal is to evaluate the strength of the handle and determine the safety factor under the most extreme loading, 3 kilonewtons at a given angle. And the diameter of the handle is 30 millimeters and the thickness of the plates are 5 millimeters. The material is stainless steel, and it's welded to the plates by using a double-sided fillet weld. So we will start by going through the geometry and dimensions of the model, then define the material properties, boundary condition, and show you how the load is applied. Finally, we are going to run the simulation and use the design study to analyze and improve the handle geometry, the curvature. Okay, so here we have the part. I have sketched a line here that is going to be representing this handle, and with the sweep I have created a diameter of 30 millimeters, and this angle here is going to be varied in the design study. I have created another sketch here. I'm going to hide this sketch now. This sketch is for the direction of the force. It's 15 degrees here, and I have divided this surface for the force to be applied with this command here, and then I create the plates here with 15 millimeter thickness. I have used this cavity here to cut through the planes with this part. Okay, so when you create a new static study, you go to the connections here and you delete everything, because we were going to weld this here. And let's just apply a material for all the parts here. This stainless steel, apply. And now when we are going to, now we have 3 bodies here, and every one of them are going to be defined as shelled. A thick shell with 5 millimeters, and the direction is going to be this one. And let's pin this to do this quickly. Yeah. And the last one, inside surface, you choose. And then you exit you have defined the shells. The thin plates can be defined as shell elements. Okay, so now you fix the shells by fixed geometry, just inside surface or inside edge. You use that, and you apply a force to the section that we have provided with the direction that we have done. And the magnitude was 3 kilonewtons, and the direction is, yeah, let's make it a little bit bigger. Now the force is applied, the boundary condition, the shell elements. Now just the connection here should be bounded. So local interactions, automatically find the interactions and use bounded. 0. The connection is done, everything is done. Just create a mesh and see. Curvature based. And let's see. Yeah. Let's run this study. Unstable. Oh, I forgot to do the welds. So let's do the welds. So go to connections, do the weld, edge weld, and this surface, and the connections between them or interactions. European standard, the materials should be the same, stainless steel, and 3 millimeters thickness. Pin this and do the same for this side, and the interaction. Okay, this side. And finally this side. Okay. Now we can run this study now. Okay, so let's create a safety factor. And as you can see, we have exactly on the yield strength, the minimum safety factor is 1. We are going to optimize that by changing this curvature. So you go to the static, create a new design study, add some variable parameters. I have done this before. So the gamma that I have chosen, and it's the value is 36 right now. So we can cancel and add this gamma here. And let's have a range on that from, let's say, 10 degrees to 50 degrees or 55 degrees. The constraint I have done before too, so minimum factor of safety. And you can add some constraints, go to simulation data and use factor of safety or stress or anything that you want to have as your constraint. So I'm going to exit here and use one of my constraints. Minimum factor of safety. The safety, minimum factor of safety should be less than or more than 1.3. 1.23. And let's add another one, stress. It's going to be less than the yield strength. Let's say 200 or whatever megapascal. And we are going to optimize, the goal is to optimize the minimum factor of safety. Minimize this. And let's run this study now. It's going to take a while, so, or maybe not. It's only 5 studies. So let's see which angle is the preferred angle with the minimum safety factor. Or, yeah. The safety factor should be more than 1.3 and the minimum stress developed in the interaction. So the optimum is 55 degrees. And let's click on this and go to static and run this study, the 55 degrees angle. And as you can see, let's look at the safety factor. It's 1.3. And where is this 1.3? I think it's in the interaction here. Can you show the safety factor? Chart options maybe. Yeah, show maximum. No, it should be minimum safety factor. Minimum. It's in this part because we have bent this so much that it's going to be in this part. But it's okay because it has the safety factor 1.3 compared to 1 before. So if you bend this, it's better for our design study because it's going to be more tension than bending. And bending results in more tension if you have a straight one. So if you have the curved part, it's better for this study, according to our design study and how we applied the force and the geometry that we have right now in this assembly. So thank you for watching this, and I hope you learned something. Like and subscribe if you liked the video. Thank you.